Has the James Webb Space Telescope truly peered back to the absolute beginning of time? What if everything we thought we knew about the early universe is about to be rewritten? Prepare to have your mind stretched beyond its limits, because JWST has just made a discovery that's shaking the foundations of cosmology. Imagine looking at a baby photo of the entire universe, not just a snapshot, but a moving image of its very first moments. That's essentially what the James Webb Space Telescope is allowing us to do. Launched on Christmas Day, 2021, after decades of meticulous planning and engineering, JWST is an infrared marvel, precisely designed to peer through the obscuring cosmic dust and gas, and observe light that has been traveling for nearly the entire 13.8 billion year age of the universe. Its primary mirror, a colossal 6.5 meters 21.3 feet in diameter, isn't a single piece of glass, but a masterwork composed of 18 hexagonal, gold-coated beryllium segments. This intricate design, folded like celestial origami for its journey to the second Lagrange point L2, allows it to gather even the faintest whispers of light from the most distant and ancient corners of space and time. Unlike its predecessor, Hubble, which primarily observes invisible and ultraviolet light, Webb's infrared vision is crucial because the light from the early universe has been redshifted by the expansion of space, shifting it from visible wavelengths into the infrared, where Webb excels. Recently, the astronomical community has been buzzing with a groundbreaking announcement from the JWST team. They've detected a truly massive and incredibly old structure that dates back to an astonishingly early epoch in cosmic history, a mere few 100 million years after the Big Bang itself. This places its formation within the first 300 to 400 million years of the universe's existence, making it not just one of the oldest, but one of the largest and most complex structures ever observed at such a primordial stage. This isn't just a single isolated star, nor even a lone, fledgling galaxy. What Webb has found is a protocluster, a collection of galaxies in the very process of merging and assembling, or a substantial filament of the cosmic web, a vast, intricate network that forms the universe's invisible scaffolding. This colossal entity contains hundreds of nascent galaxies, each potentially teeming with billions of young, hot stars. Its immense estimated mass, equivalent to several trillion suns, is held together by the pervasive force of gravity, and it is expected to eventually evolve into a colossal, gravitationally bound galaxy cluster, much like the massive clusters we observe in the present-day universe, such as the Coma cluster or the Virgo cluster. For decades, our prevailing cosmological models, particularly the Lambda CDM model Lambda cold dark matter, predicted a slower, more gradual, bottom-up process for the formation of large structures in the early universe. The universe, immediately after the Big Bang, was a scorching hot, dense soup of elementary particles. As it expanded and cooled, approximately 380,000 years after the Big Bang, protons and electrons finally combined to form neutral hydrogen atoms. This event marked the beginning of the cosmic dark ages, a period stretching for hundreds of millions of years, where the universe was largely opaque to light, devoid of luminous stars and galaxies. It was only when the very first stars, known as population 3 stars, ignited, releasing intense ultraviolet radiation, that this cosmic fog began to dissipate in a process called reionization. Our previous models suggested that large, complex structures like this newly discovered protocluster would only begin to fully coalesce after reionization was well underway or completed. This new discovery by JWST, however, suggests that significant structural development was already well on its way to forming during, or perhaps even before, this reionization process was fully complete, indicating an unexpectedly rapid assembly of matter. To truly grasp the magnitude of this discovery, we need to understand the concept of the cosmic web. Imagine the universe not as a uniform, evenly distributed expanse, but as a vast, three-dimensional, intricate network resembling a spiderweb, or perhaps a colossal sponge. This web is the largest known structure in the universe, a gargantuan scaffold composed primarily of invisible dark matter, which makes up about 27% of the universe's mass and interacts only through gravity, and vast, diffuse reservoirs of ordinary baryonic gas. Galaxies, and subsequently the grand galaxy clusters we observe, are thought to form within the denser knots and along the filaments of this web, drawn together by the immense gravitational pull exerted by the dark matter scaffolding. The immense voids in between these filaments are largely empty. Finding such a large, complex, and seemingly mature structure so incredibly early in the universe's history implies that the cosmic web was already establishing its grand architecture and gravitational attractors on a massive scale much earlier than previously believed, providing the necessary density enhancements for galaxies to rapidly clump together. How can JWST see something so incredibly old and distant? practically at the dawn of time. It's all thanks to a combination of groundbreaking technology and fundamental principles of physics. The first principle is the expansion of the universe and the resulting phenomenon of redshift. As the universe expands, the very fabric of spacetime stretches, and light waves traveling from distant objects get stretched along with it. This stretching lengthens their wavelength, shifting them towards the ray and eventually infrared end of the electromagnetic spectrum. The farther away an object is, the more its light has been redshifted. JWST, specifically engineered to detect this highly redshifted light, operating in the near-infrared and mid-infrared wavelengths from 0.6 to 28 micrometers. This specialized infrared vision is not only crucial for detecting redshifted light, but also allows it to penetrate the thick veils of cosmic dust and gas that would completely block visible and ultraviolet light, effectively acting as a powerful time machine allowing us to observe the universe as it was billions of years ago. Another incredibly powerful tool in JWST's observational arsenal, often used in conjunction with its infrared capabilities, is gravitational lensing. According to Albert Einstein's revolutionary theory of general relativity, massive objects, like giant galaxy clusters, can warp the very fabric of spacetime around them. This bending of spacetime also bends the path of light that passes near them, much like a giant, natural cosmic magnifying glass. When a distant galaxy or structure is serendipitously positioned directly behind a massive foreground object, the lens, its light can be magnified, brightened, and even distorted, sometimes creating multiple, stretched, or arc-shaped images of the same distant object. JWST frequently takes advantage of these natural lenses, using their magnifying power to peer even deeper into the early universe, observing objects that would otherwise be far too faint and distant to detect with even the most powerful telescopes. This cosmic magnification provides an invaluable boost, effectively extending Webb's already incredible reach into the primordial cosmos. The astonishing existence of such a massive structure, already containing hundreds of galaxies, at such an incredibly early stage of the universe's development fundamentally challenges our existing theoretical models of hierarchical galaxy formation. These long-standing models proposed that galaxies begin as relatively small clumps of gas and dark matter, which then gradually grow larger over billions of years through a process of accretion, violent mergers with other smaller galaxies, and collisions. This new discovery, however, implies that either the initial seeds for these structures were much larger than previously expected, or that the growth process was significantly more rapid and efficient in the extreme conditions of the early universe. It suggests that the environment shortly after the Big Bang may have been conducive to extraordinarily fast assembly of matter, perhaps through more direct collapse mechanisms or by a surprisingly early and efficient cooling of primordial gas. This forces cosmologists to re-evaluate the initial conditions and timescales of galaxy assembly, pushing the envelope on how quickly complexity can arise in the cosmos. The rapid formation of such a large structure also brings into sharper focus the crucial, though still largely theoretical, role of the very first stars, often referred to as population 3 stars. These hypothetical stars are thought to have formed out of the pristine gas left over from the Big Bang, almost entirely hydrogen and helium, as heavier elements like carbon, oxygen, and iron hadn't yet been forged. Current models suggest these population 3 stars were likely incredibly massive, hundreds, even thousands of times the mass of our Sun, extremely luminous, and remarkably short-lived, burning through their nuclear fuel in just a few million years before exploding as colossal supernovae. These supernovae were the universe's first cosmic factories, forging and then dispersing the very first heavy elements into the interstellar medium. The presence of a large, early structure suggests that these population 3 stars, and the subsequent processes of chemical enrichment and reionization they initiated, might have played an even more fundamental and rapid role in shaping the early cosmos than previously theorized, potentially influencing the gravitational collapse of gas into galaxies at an accelerated pace. The period between about 380,000 years and roughly a billion years after the Big Bang is famously known as the Cosmic Dark Ages. During this epoch, after the initial burst of light from the Big Bang which we see today, is the cosmic microwave background. The universe was filled predominantly with vast clouds of neutral hydrogen gas. This gas absorbed most forms of light, making the universe largely opaque and literally dark to conventional telescopes. JWST's unique ability to see through this cosmic fog by observing in infrared light is truly revolutionary. By detecting and studying structures like this newly discovered massive protocluster, scientists can gain critical insights into precisely when and where the universe began to reionize, the process by which the intense ultraviolet radiation from the first stars and galaxies stripped electrons from the neutral hydrogen atoms, making the universe transparent again. This allows astronomers to pinpoint the timing and nature of the cosmic dawn, shedding unprecedented light on how the universe transitioned from a dark, opaque, and relatively simple state to the transparent, luminous, and structurally complex cosmos we observe today. While this discovery is fundamentally about the large-scale structure and evolution of the universe, it carries fascinating, albeit indirect, implications for the potential for life beyond Earth. The presence of complex chemical signatures within these ancient galaxies, inferred from the light they emit, and the surprisingly rapid formation of massive structures suggests that the fundamental building blocks for subsequent generations of stars, planets, and potentially life itself were available much earlier and perhaps more abundantly throughout the early universe than previously believed. The detailed spectroscopic analysis of light from these ancient galaxies can reveal the presence and abundance of heavy elements, anything heavier than hydrogen and helium, which astronomers call metals. The early and efficient enrichment of the universe with these elements is a crucial prerequisite for the formation of rocky planets, the very foundations upon which life as we know it can emerge. If the universe was capable of forming such large, chemically rich, and gravitationally mature structures so early, it opens up tantalizing new avenues for speculation about the earliest possible emergence of habitable conditions and, potentially, life itself, across the vastness of the cosmos. This monumental discovery is just one of many groundbreaking revelations that the James Webb Space Telescope is consistently delivering. Its ongoing mission, which includes surveys like JWST Advanced Deep Extragalactic Survey that precisely measure the redshifts of these incredibly distant galaxies, promises to continue pushing the boundaries of our knowledge, unveiling even more secrets from the universe's deepest past. We are truly living in a golden age of astronomy, with Webb acting as our ultimate cosmic archaeologist, meticulously digging through layers of cosmic history. Scientists are now rigorously studying the faint light from this newly discovered structure, looking for even finer details, its spectrum that can reveal its exact chemical composition, its temperature profile, its internal dynamics, and its precise evolutionary stage. Each individual photon captured by Webb carries information from billions of years ago, allowing us to meticulously reconstruct the universe's autobiography, chapter by astonishing chapter. The sheer precision and depth of Webb's observations are allowing us to test and refine cosmological theories that have been debated for decades. The universe, it seems, continues to surprise us at every turn. This 13.8 billion-year-old structure, so brilliantly unveiled by the James Webb Space Telescope, stands as a powerful testament to the dynamic, incredibly active, and surprisingly rapid evolution of the cosmos. It doesn't just fill in missing pieces of the cosmic puzzle, it challenges our long-held theories, expands the very limits of our scientific imaginations, and offers a tantalizing, direct glimpse into the fundamental origins of everything we know and perceive. It's a stark reminder that the universe is far more complex, vibrant, and active in its earliest stages than we often concede. The journey of scientific discovery is, by its very nature, never-ending, and with revolutionary instruments like JWST leading the charge, we are constantly pushing the boundaries of what humanity can comprehend about its cosmic home. What other profound secrets will Webb show us next? Only time, and like traveling across billions of years of expanding space, will truly tell. So, stay curious, keep looking up, and make sure to subscribe to our channel for more incredible updates from the cutting edge of space exploration and the latest cosmic revelations.